Hello everyone and welcome to the next session on quality control methods for herbal drug evaluation. So in this particular week we have seen different methods of evaluation and more particularly chemical method of evaluation. Right now we have finished organoleptic, we finished macroscopic, microscopic, physical methods of evaluation. When coming to chemical methods of evaluation, if you recollect, we saw that the chemical methods of evaluation were broadly classified into two categories, that is the qualitative methods as well as the quantitative methods. So when we discussed the qualitative methods, we did something called as phytochemical test, microchemical or histochemical evaluation, limit test as well as thin layer chromatography as a way of qualitative analysis to tell whether a particular compound is present or not, or whether a drug is genuine or not. We then went on to quantitative method, wherein we started quantifying certain things, especially the phytochemicals. So we saw last time a UV method. So we did see last time a UV method as well as a fluorimetric method for quantification of certain compounds like quinine, flavonoids like quercetin and so on. So in this particular session we will dwell into the next one, and that is understanding how we can do quality control of herbal drugs using chromatographic techniques. So doing chromatographic techniques, there are different chromatographic techniques which are involved. This includes your HPTLC, this includes your HPLC, and this includes your gas chromatography. So numerous other chromatographic techniques are involved, but we will focus our interest into these three techniques. We will start with the first technique of evaluation, and that is HPTLC. HPTLC stands for high performance thin layer chromatography. So if you just recollect from your previous session where we did qualitative analysis, we did see that you can run a TLC plate, and this TLC plate, depending upon the polarity of the compound, you get what is called as RF or retention factor. Now in this particular session we will try to understand that can the same plate be used for quantification of compounds and how. So the quantification of compounds can be done by HPTLC if you follow a particular technique and if you have a standard with you. So if you have a standard to compare, you can definitely measure how much compound is there in your extract. So for it, a quick stepwise sequence would be, the first step is you take your material of interest. Now this material of interest can be a herbal drug, it could be a herbal preparation, it could be a herbal medicine, polyherbal formulations, or in some cases even substances which people claim as herbal or natural. Say for example your herbal shampoos, wherein the amount of actives or herbals added is very less, but still are they being added or not, and how much they have been added, we can still quantify them with help of HPTLC. So you start with any sample of your interest. The next step what is involved is sample preparation. Now this sample preparation from your sample matrice, be it plant, be it formulation, be it any preparation. So from that particular matrix you are going to extract the compound of your interest or the compound that you are going to analyze. These are your simple marker compounds, what they are referred as your phytochemical reference standards. If you recollect, they are very unique for a particular plant, and that can be used as your marker compounds. So these phytochemicals which are unique to a particular plant, which are often referred to as marker compounds, are used as standards for analysis. Say for example, I am analyzing ashwagandha preparation. A good a standard or a good marker for me to analyze ashwagandha preparation would be Vidaferin A, which is more unique to ashwagandha rather than having something like your gallic ellagic acid, which is seen in different or numerous other plants. So if I pick up unique marker, that will kind of tell me that yes, this preparation is showing me ashwagandha spot for Vidaferin, and since it is showing Vidaferin, definitely it has ashwagandha. So I will prepare my sample in a way that I can take Vidaferin out, or I can extract Vidaferin out from my ashwagandha raw material or from any ashwagandha kadha, syrup or tablet. I should be able to do that using suitable solvent. Now once this solution, that is your sample, is ready, that is your ashwagandha extract is ready more specifically, it is then applied on a TLC plate. Now when you do a normal TLC, we generally apply with hand because it's qualitative. We are not interested in the quantity. In this case, we are interested in how much is applied, and we just have to apply a very specific calculated amount because we are going to take the readings from it. So this is done by a machine controlled manner called as applicator. So then you have an applicator, a machine which applies the spot in a measured quantity at a measured volume. Then you run your plates like you run your TLC plate. Then important step which differs in your TLC versus HPTLC is you are going to use this plate for quantification by scanning it. What do you scan in the process? You scan the intensity of the spots. So you can see here, I can see some spots which are very intense here, and then the spots here as well as below are very light. So when I am scanning the intensity, do you come to see this? So there is a corresponding peak. So this two peaks, peak number 1 and 2 correspond to this two peaks. This is 1, this is 2. So you can have these two peaks here and these two peaks here. You know they are more intense. So here you can see the peak height as well as the peak area under curve is also higher. Okay. So if this happens to be my area or this happens to be of my compound of interest, I am going to measure the area under curve of this particular substance. Then I am going to plot it, peak area versus concentration, how much did I apply, and then what I get is a very linear curve very similar to that of UV. So in that manner I can carry out my quantification. But yes, there are few critical things that we need to understand. So let's try to understand them one by one. So the first thing, or the first and the most important step, is sample preparation. So from the plant, say ashwagandha, from your tablets, from your preparations, from your thick viscous syrups, how are you going to prepare it? The key considerations I should keep in my mind is, in my plant, in my tablet or in my syrup, what is the concentration of my phytoconstituent that I am trying to determine? You might have a liter of a formulation having just 1 mg of Vidaferin, or you might have a kg of plant material having a very minuscule or microgram levels of a given compound. So if I have to quantify that, how much sample do I take to extract that particular compound is, or that will be the deciding. So if the concentration is less, you will have to take a large volume of samples. On the other side, if the concentration is very high, say 2%, 5%, in that case, even if I take 1 gram of sample for my analysis, it's perfectly fine. But if my 1 mg is there in about, a kilo of substance, I'll have to extract a kilo of that formulation or a liter of that formulation in order to get 1 mg of my analyte compound in my extract. So you all see the concentration first, and depending upon the concentration, you have to take a call how much sample do you need to take. And that will be decided by the concentration, which you have to find out by literature, or you have to find out based on the what is called as the label of a formulation. So if the label claims your ashwagandha extract is 1%, so you do a little back calculation how much ashwagandha is going to be there in the extract, so how much ashwagandha is going to be there in the final formulation. So once I do that, it becomes much easier for me to take a estimate of what quantity of sample do I need to extract. The next thing what determines the sample extraction is the solubility. How much is the solubility in the given solvent? So we do use what is called as like dissolves like. So if it is a polar compound such as tannin, I use alcohol. If it is a non-polar compound like your carotenoid, lycopene, we just saw, they are extensively lipophilic. You can use your petroleum ether, you can use chloroform or benzene and so on. The next thing is, when I am preparing the sample, is my compound stable? In some cases, when we saw your alkaloids, we said that basifying it could extract them better in organic solvent. But are they stable to bases? We will also have to check that. So you also have to check stability of your compound. Certain compounds like your anthocyanins, you cannot heat them. For other processes, you might involve heat to get a better extraction as heating increases solubility. But there are certain compounds like anthocyanins, if you heat them, they will brown or they will turn dull and they will deteriorate. In that case, you will have to do a cold extraction. So you have to see the physical as well as the chemical properties of the compound that you are analyzing. Now, different methods are involved, such as maceration or percolation, but a very good method to extract the substance or a formulation completely is what is called as Soxhlet method. So, Soxhlet method uses Soxhlet assembly. We will not go deep into extraction here, but the Soxhlet assembly acts in a way that you always are, or the sample is always subjected to fresh solvent, and as a result a complete extraction of your component happens. So you need not worry about the volume of solvent. The assembly will recycle the same solvent and extract more and more of your compound. So most of the analytical methods where your compound is heat stable, the sample preparation is done using Soxhlet assembly using a suitable solvent. Then you have to also see the nature of impurities present or other substances present. Imagine you are trying to extract something which is water soluble, but your substance, especially your drug, is lipophilic, it is oily. So what will going to happen is that oily nature of the drug will kind of hinder the extraction of your polar compound. So first you might require to defat it. In some cases where the pigments are very much intense, so much so that your actual compound will not be seen unless and until you remove the pigments out, like chlorophyll, or in beetroot there are your betalains. So this deep color pigments often hinder with extraction and sometimes even with detection. So in that cases it's always good to kind of get rid of them using the solvent which will selectively remove your pigments, fats or other impurities, and thereafter what you are left is with a simple solvent like alcohol to extract your analyte of interest. So you can choose a solvent, say for example if you are extracting tannins from your Triphala churna. Now you know Harda, Beda, Amla, all of them have gallic, ellagic acid and they all have good solubility in alcohol. So I can just take the whole Triphala churna, mount it in my or load it in the thimble of my Soxhlet assembly and thereafter extract it completely till no more tannins are coming out. Then I concentrate it and I can use this extract for my HPLC analysis. So this is with the sample preparation. Now we go to sample application. Now sample application is done with a, if you can imagine this is more like your printer. So it's like your inkjet printer. So what you can see here is a syringe. So this syringe is filled with your extract and then this syringe is controlled. This is kind of a 100 microliter syringe and you can control the rate. That is, on the plate I just want to spray 1 microliter. On the next spot I want to spray 2 microliter. So I can effectively control the volume that I apply on the plate, which doesn't happen with hand. So this kind of assembly uses nitrogen or inert gases to create the fine mist of the extract and then sprays or kind of prints your extract on the TLC plate. So you can see here there is a TLC plate and this is the syringe nozzle. So syringe nozzle is also laced. You can see this tubing. This tubing is of nitrogen gas. So this nitrogen gas helps kind of nebulize it into a tiny droplets, and this tiny droplets are applied here. This plate, this steel plate moves, and as a result the application is more effective here. Now once you decided to apply it, you will have to take few key considerations in the mind. First thing is the extract concentration. If the extract is too much loaded, it causes tailing. So I should have or use my extract optimally. In many of the cases, people often apply extracts in 3 different concentration, like 5 microliters, 10 microliters and 15 microliters, just to be sure that at least one of them will be running very smoothly. Then you have to plot a standard curve. This is quantification. So you have to also apply along with your extract your standards in a particular concentration, like 2 microgram, 4 microgram, 6 microgram and so on. So those spots are also placed simultaneously on the plate. Then you have to see that because this is a syringe and it's very fine, creates a very fine mist, your extracts, if you see your herbal extracts, they are sticky and they often precipitate compounds which will often tend to block the needle of your applicator. So always filter your extracts, and there should be no particles for a very seamless application. Otherwise, what is going to happen is if there is a particle, it will obstruct the flow and create a blob later on if it is kind of blocking your syringe. Once your sample is applied, you go for a plate development. The plate development is very much similar to that you saw in your TLC. You remember there is what is called as your TLC chamber. Now this TLC chamber is covered to prevent the evaporation of your mobile phase. The mobile phase is often placed below. In some cases you have a single trough. In some cases you might have something like this is called as a twin trough, wherein you can save or store the solvent in particular layer as well. Generally they are equilibrated, and what is done is, in order to achieve chamber saturation, your filter paper is applied. Now what does the filter paper do? Filter paper will absorb all the mobile phase and then it will easily diffuse it in the chamber, causing a instantaneous chamber saturation. So your chamber will get saturated, and once the chamber is saturated, then you run your plate. So you can place your TLC plate here on which you have applied the spot, and then they will run. Now if this is your normal phase TLC plate, like your silica plate, most of your non-polar compounds will be on top and your polar compounds will be on the bottom, because your stationary phase is polar and your mobile phase is going to be non-polar. Now there are few additional things when herbal extracts are taken into consideration or applied. Now you might see that apart from silica, there are other stationary phase such as alumina. You can even have cellulose base. These are used to separate different type of constituents. Not only that, you can change your mobile phase depending upon the compounds. So say for example, I have alkaloids. A good or more universal mobile phase for alkaloids is toluene ethyl acetate diethylamine in a ratio 7:2:1. Now the reason why you use diethylamine is something that we discussed earlier. So if you see alkaloids, these alkaloids are present as salts. So if a compound is present as salt, imagine something like your NaCl, what is going to happen is the salt form is extensively polar. So it will tend to stay here. So what do is you basify it. Now when you basify your alkaloid, the alkaloid will no longer exist in the salt form. It will exist as a free base form, and free base form is more non-polar. So instead of binding here, when I am using a mobile phase using diethylamine, it will basify the alkaloid and as a result cause it to move because it increases its unionized nature. Similarly, if you talk about flavonoids or if you talk about tannins, what happens is these are acidic substances. So if I am just using it as such, again because of their polarity they will tend to bind in this region. But imagine if I have a mobile phase which has a little bit of acid, glacial acetic acid or formic acid, you will often come across this in those mobile phase. So what happens now, this flavonoids OH and as tannic acids or your tannins COH all are in unionized nature. If they are unionized, they are going to run well, and that is the reason why most of the alkaloidal mobile phases have amines in them, as well as the flavonoid and tannins based mobile phase have acids in them. Now apart from that, if you have more neutral substances like volatile oil, you can have an extensively lipophilic mobile phase like a toluene ethyl acetate, where toluene is as high as 93% and just a small amount of ethyl acetate, that is 7%, is added. Important key consideration for a good TLC plate is the chamber saturation should be good and it should be at a constant temperature, preferably at a lower temperature. The reason being your solvent should not volatilize and escape from the plate. Now once your plate is developed, we go to the next step, and that is visualization. So how do you see the plates or how do you see the spots? Now in many of the cases where your compounds are colored, take for example this. Here I can visually see the compound because my compounds are colored. So even putting it under a white lamp is going to help me out. But imagine if the compound is not colored, something like your paracetamol, aspirin, or take for example your alkaloids like your quinine, they are not colored. So when I run the plate will be entirely white. I don't see any color on them. So in that case I need to have what is called as derivatization. So either I do a detection using UV vis or I do a derivatization. Now what is this detection using UV vis? Now under visible light certain times the compounds are not visible, but when you put it under UV light, especially there are two UV lamps in your TLC viewing chamber, that is one is at 254 nanometers and another one is at 365 nanometers. So this two lamps, there is a reason. Many a times your TLC plate contains a fluorescent substance which fluoresces at 254 nanometers, and then what happens is your aromatic substances quench on them. We'll subsequently see the example of that, whereas at 365 is more of a purple or a violet UV region which is more which gives you more of a fluorescent substance or a fluorescent glow in some substances. Not only that, there are compounds such as aflatoxin which will fluoresce when you put it under UV 365 nanometers. Now despite this, a better way to see it under normal light or white light is derivatizing. So there are certain reagents which will react with your phytochemicals to give you different colors, and these colors can be seen visibly. Say for example your alkaloids, you remember we used Dragendorf's test. In the same manner, this same Dragendorf reagent, if I dip my TLC, will give you an orange color. For polyphenols, you remember you had your ferric chloride test for tannins. Similar plate, if you dip in, all your tannin bands will become bluish green in color. Volatile oils, you all can treat it with what is called as anisaldehyde sulfuric acid or vanillin sulfuric acid reagent. However, these reagents are not reactive at room temperature, so you might have to heat a plate for about 5 minutes at a temperature exceeding 100. So they will gradually get derivatized and you will see different colors of terpinaceous compounds. Flavonoids, you can derivatize it with a natural product reagent. If you are not sure about what compound there are and if you just want to detect non-specifically, you can keep it in the iodine chamber, wherein iodine vapors react with any compound which is unsaturated. That is the double bonds, and then those bands become yellowish in color. Not only that, even if the compound is saturated, you can still detect it by charring it with sulfuric acid reagent. So let's see a few examples herein. So this is a UV plate of black pepper fruits. So when we run this black pepper, especially in toluene ethyl acetate, what happens here is, you can see at one spot I have marked my standard piperine, and at 2 I have my black pepper alcoholic extract. So you can see standard piperine is just a single band, and this black pepper fruit contains numerous compounds. Now this I am seeing under UV 254. So my plate has a fluorescent indicator which fluoresces the whole plate, but the moment there is any aromatic compound on top of it, it's going to quench, and that quenching is going to result in dark color spots. That means in that region the fluorescence cannot reach my eye because these compounds are going to absorb it. But now if I see the same TLC under UV 365, what happens herein is, you can see the same spots which earlier quenched now produce a faint glow or a fluorescence. Take the same plate and then dip it in Dragendorf reagent and slightly wash it with water. What happens is, your Dragendorf reagent is little orangish, so it renders an orange color. Moment you kind of wash it with water, the orange color remains only on places where alkaloids are present. So when you see so many bands, what is happening is, you are telling that definitely there are so many compounds which are seen. Here you can see even more. So in the UV there are more in the visible region also. If you see the tiny amounts, some of them have not run in. So UV region shows you so many bands, but the moment I derivatize and I wash it and I see it under visible region, what I see is a faint piperine standard which is orange, and this is the piperine extract. What does it mean? There are remaining other compounds are not alkaloid. Similarly, I can do a TLC and check for the presence of aflatoxins. So this are aflatoxin standard B1, B2, G1, G2, and if you see different samples, you can say that they have been contaminated with aflatoxins because they show a fluorescence at a very same RF. Now once we do the visualization, the next step is scanning. The scanning is often referred to as densitometric scanning because it measures the density of the spot being there. Now just take example, now this is your solanum, and in your solanum you have different alkaloids such as your solasodine, solasonin and solmargin. Now in that case, what is done is, I am using mixed standards of different concentration. So I am going to prepare a standard curve for, say for example, solasodine. I am going to say here area under curve, and I am going to write here as concentration. So this is the concentration of 2 microliter, 4 microliter, 6 microliter, 10 microliter, something like that. Now what happens is, when I prepare a standard curve, I might get something called as a good linear observation. So at higher concentration I will have higher area under curve. Now what I do is, I spot my plant extracts. You can see here 24, 25 are your plant extracts. Now when I see that, I measure the intensity here. The intensity, it's something like your area under curve of this particular chart. Now if I see this area under curve and I plot it, I get the concentration in a very similar manner. So I can do I can quantify my compounds using HPTLC, but the only thing that I require is, I'll require my standard of solasodine to quantify solasodine. Similarly, if I have solasonine standard, I can quantify that as well. The thing is, it can all happen simultaneously. What one more parameter I need to check is the values which is required for validation, and that is LOD, LOQ, linearity. I am just emphasizing on this, but there is ruggedness, robustness and so on. So what is this is, whenever you try to quantify, there is something called as slope of this curve. Now if you take what is called as standard deviation of this values, whatever you are getting in your standard curve. So if it is like 3.3 times standard deviation, if you divide it by slope of this, is what is called as your LOD, that is limit of detection. That much quantity you can detect. And LOQ is a value which is often given by 10 times standard deviation of this values divided by the slope. So, you should see that when you are quantifying them, your quantity of the extract. So, this spot should be higher than LOQ. If it is not, you have to reapply and do the measurement one more time. Now, here are few examples. So, you can see here your chlorogenic acid. You can see this is the standard, and that can be visualized using different reagents. Okay. So, you can visualize it under UV. You can visualize now what has happened here. Here you have applied a NP or natural product reagent, and this is under normal daylight. So, you can see it is a very faint thing under normal daylight, but if you apply a derivatizing agent, you can see the color intensity much better, and for quantification you would definitely prefer this plate over this plate. Similarly, I can detect curcuminoids if I have standard curcuminoids with me, and then I can apply different turmeric samples. I can see them under UV 254, I can see them under visible, that is normal light, or I can derivatize them. You know your haldi, that is turmeric, when you add any alkali, they become red in color. So, you can use alkali, or you can even derivatize it with something like your anisaldehyde sulfuric acid to get a colored. So, this is after derivatization. So, you can quantify this plate at this wavelength or even at this wavelength. In some cases it can be quantified, and then you see where the intensity of those peak is more. Wherever the intensity of that peak is more, always use that wavelength for measurement. Not only that, in certain cases spices, we just saw ASTA values. Sometimes people deliberately add inks or dyes to it. So, you can see here they have spiked it with different colorants, and your HPTLC is able to make out even the most dilute version of the spiked colorants. So, you know, it's just 2 ppm which is spiked in that colorant. So, still you are able to identify versus your natural sample. Okay. So, now going on to few more applications, your HPTLC based on the fingerprint. So, if I know that this is going to be my fingerprint of Solanum, I can just use this fingerprint and analyze another plants. If another plants are showing the same pattern, there is a good chance it is Solanum. But if it is showing slightly different bands, what does that mean? It is another plant or another species. Okay. Then you can quantify the phytoconstituents we just saw. You can validate and standardize the raw material. There is a lot of variation happening at the raw material, even if you take it from different geographical places, or even if you take it from different seasons. Your HPTLC will help you quantify the actives and tell you how much variability is happening. Not only that, we just saw it with colors. So, you can detect adulterations, you can detect another plant species, you can detect if like your methyl salicylate, whether it is a natural methyl salicylate or a synthetic one. Synthetic one will have more of your salicylic acid as an impurity, whereas your methyl salicylate, that is your wintergreen oil, will show more of your monoterpene bands in that. So, you can know that which oil is natural, which oil is synthetic. Not only that, you can detect your aflatoxins, and yes, you can quantify this not only from the plant matrices but also from the herbal materials. So, here are a few more references if you wish to understand more about HPTLC as a method of quality control, and thank you everyone for your patient listening.